Pragathi Praveena, and I will be presenting our work on understanding control frames in multi-camera telemanipulation. Using robot teleoperation, people can accomplish tasks in remote, hazardous, or high-precision environments. A typical teleoperation interface will show the user views from multiple vantage points. These multiple views can help the user understand scale, depth, and spatial relations between elements in the remote workspace. But controlling a robot using multiple viewpoints can be a challenge. Here is an example of why that is the case. Consider this mobile robot that can be teleoperated by a remote user. There are two cameras on the robot, camera 1 at the front of the robot and camera 2 at the back of the robot. The two cameras cover different areas of the robot workspace and both are necessary for successfully teleoperating the robot. The remote user sees these two camera feeds on their interface, view 1 from the front of the robot and view 2 from the back of the robot. The user can give input to the robot using a joystick. The joystick's control frame is the frame of reference in which the user provides motion commands. In this example, the control frame is aligned with the robot's coordinate frame. So pressing the right arrow on the joystick moves the robot to its right. Let's now look at the front camera view. We want to see what is on this side of the robot. We command the robot to move in that direction by clicking on the right arrow. Oh, there's a plant over on that side. Let's now look at the back camera view. We want to see what's on this side of the robot. Similar to before, we command the robot to move in that direction by clicking on the right arrow. But wait, the view is moving in the opposite direction. Why? Remember that the back camera faces the opposite direction to the front camera, so it's like a mirror image. That means if we want to see what's in this direction, we must give an inverted input. So we click on the left arrow and we see that there is a chair on that side. There is an inconsistency here. When looking at the front camera, moving in this direction corresponds to the right key on the joystick. When looking at the back camera, moving in the same direction corresponds to the left key on the joystick. Because these two cameras are in opposite directions, there will always be this inconsistency. So when looking at the back camera, the user needs to invert the direction to give the right command. It is very likely that in a multi-camera interface, there are at least some views where the direction of user input is inconsistent with the view. In this case, the user has to perform mental transformations to give the right command. This inconsistency is a challenge in controlling a robot using multiple viewpoints, and we address this problem in our work. There is some prior work that suggests that if the user is allowed to use a different control frame with each view, they can be more successful at teleoperation. Each control frame maintains consistency between the user input and the view. These prior works consider simple camera configurations and inputs. In our work, we want to extend this understanding of using multiple control frames to broader scenarios where there may be complex camera configurations and systems that require a full 6 degrees of freedom input. That brings us to the research question. How do control frame choices in a multi-view interface affect teleoperation performance and user experience? At the crux of answering this research question are the costs associated with various control frame choices. We identified 3 costs: inconsistency, control burden, and loss in momentum. We've already discussed the inconsistency that can sometimes exist between the view and the direction of user input, which requires additional mental transformations for control. This can increase the user's cognitive load and reduce task performance. The second cost is the control burden associated with selecting the control frame that the user wants to use from the available options. The user has to indicate when and which control frame they would like to select. This is an additional input that the user must provide to the system to be able to switch between multiple control frames. The third cost is the loss in momentum. Consider the mobile robot example where the two view-aligned control frames were mirror images of each other. Suppose the user selects this control frame and presses the right key of the joystick, the robot will move to the right. If the user switches to the other control frame and continues pressing the same right key, the robot will now move to the left. This is what we call a loss in momentum. For the same user input, the robot starts to move in a different direction when another control frame is selected. So when the user switches from one control frame to another, they have to additionally modify their input commands so that the robot continues to move in the same direction. We use these costs in the formulation of our 2 hypotheses. Our first hypothesis is that, compared to the standard use of a single fixed control frame, allowing the user to switch between multiple view-aligned control frames will result in better task performance and user experience. The use of a single control frame results in high inconsistency and no switching costs. The use of multiple view-aligned control frames results in negligible inconsistency and some control burden and loss in momentum. We expect the total cost to be lower with multiple control frames and thus expect better outcomes. Our second hypothesis is regarding selection of the control frame when there are multiple frames. We consider two mechanisms for selection. The first one is manual selection by the user pressing a button. The second is automatic selection based on the view that the user is currently seeing. We infer the user's current view in our work using eye gaze data. Our hypothesis is that compared to manual selection, automatic selection will result in better outcomes. During manual selection, we expect the control burden to be a significant cost because of the already high cognitive demands of telemanipulation. We expect this cost can be reduced with automatic selection. We expect the total cost to be lower with automatic selection and thus expect better outcomes. In the next section, I'll discuss the user study that we conducted to test these hypotheses. In our user study, participants controlled a robot arm in a simulated workspace using live video feeds from 3 cameras. Participants used a full 6 degrees of freedom input device. For manual control frame selection, users pressed a button on the same input device used to give motion commands. For automatic control frame selection, we used an eye tracker to infer the user's current view and automatically switch to a control frame aligned with that view. We conducted a within-subject study where participants completed 3 conditions using the 3 control frame choices in our hypotheses. We recruited 24 participants. For each condition, they completed a training task followed by 3 tasks situated in a home care scenario, such as cleaning up, serving a meal, and prepping a meal. This is an example from part of the meal prep task completed by a participant. Our results show support for the use of multiple view-aligned control frames compared to a single control frame. Task score is one of our measures, and we see significantly higher performance scores for the 2 multiple frames conditions. However, we did not find any statistical differences between the 2 mechanisms of control frame selection for any of our task performance or user perception measures. Because we observed a high variance in the measures across participants, we did an exploratory analysis using motion and eye gaze data, as well as responses from participants regarding their planning and execution strategies for each condition. Our exploratory analysis identified groups of participants who had similar strategies for planning their movement and strongly favored one of the 3 conditions. Only a small group of participants were able to complete tasks using a single control frame. They were able to successfully reconcile the inconsistencies between their inputs and views and benefit from not having any switching costs associated with multiple frames. The rest of the participants preferred the option to switch between multiple control frames. Participants who favored manual selection did so because they were sensitive to the loss in momentum. With manual selection, they had more control over the switching process. One group made a minimal number of control frame switches, only when they deemed the switch absolutely necessary. Another group preferred to have time to think and prepare for the loss in momentum. For both these groups, the loss in momentum during automatic selection outweighed the control burden of manual selection. Participants who favored automatic selection experienced a significant reduction in control burden. One group switched control frames very often and benefited from automation. Another group was engrossed in the manipulation task and preferred not having to think about the control frame switch. Both these groups experienced lower control burden due to automatic selection. The first main takeaway is that it is beneficial to allow users to switch between multiple view-aligned control frames. The problem with a single control frame is that users have to integrate information from various views with different frames and maintain a global spatial mental model of the robot's workspace. Multiple control frames allow users to work in a local frame of reference without having to maintain global spatial awareness. The second takeaway is that there are costs associated with multi-view control frames, and the trade-off between these costs can differ based on user strategy. Both manual and automatic selection of control frames are feasible approaches that can be beneficial in different ways depending on the user. Thank Thank you for listening.